person that didn't make it running with JavaFX, but that was a JavaFX issue, and yeah, simply my fault is that there was like easy fix for OpenJDK for Ubuntu, but seems not maybe for all versions, but there was nothing for Mac. I forgot about it. Yeah, but basically this is a Java issue, not an ETA at all. And for their solution, by the way, I actually prepared myself for non-working ETA and JavaFX actually. And as far as I remember, you can as well do ETA code run. And then, just a moment, this runs totally everything in Haskell, so you have this displayed this way, without JavaFX. This doesn't touch, but the point is, it doesn't touch Java code at all. Everything happens in this main method here. But okay, so we are back. We stopped with making this funny simulation of game of life. I encourage you to, if you have some, let's say, you can make experiments with, for instance, what if I put here like 2 and 4 neighbors? Because strange things happen, actually. I cannot promise it will be anything sensible on the screen, but sometimes you get a very, this is actually a valid thing. The original game of life had some, so yeah, now it works actually. Yeah, you see that it's not really beautiful, but it's a different algorithm. But actually, a lot of them make sense, like are funny, and are even used for experiments. Because this is like used for some simulations, predicting stuff. I don't really know. This is like whole science behind game of life. The point I wanted to show you with that how we connect with Java to Haskell and back, and I actually haven't shown you that part. So let's see. If you go to the class called LifeJay, LifeJay, this is it. So I called it to separate, this is a module actually, language module. So in Haskell the files are modules. You have these declarations. And LifeJay in my case means this is like binding from Haskell to Java. So almost everything in this file is about how to connect to Java. For instance, this definition. Who knows what it can be? Okay, this is how in Haskell say that there is a class in Java AWT color. Basically, it represents RGB color. This is in Java. This is well-known Java class from standard Java library. And now we can refer to this as JColor in Haskell. Simply, there will be a type JColor, and we declared it. This is more or less the same story. Whenever there is like new generation, I publish it as like a kind of a bitmap. Bitmap in Java, let's say this is like writable image, so image. And again, this is a well-known Java FX class. And again, we can this way have it in Haskell. Same with pixel writer. Now, more interesting, we only defined types. Now, what if I wanted to see what is the green or red or blue part of this color there? And there is for this here is called foreign import and means that there is a method getGreen in Java color. Here may be interesting. This Java here is kind of a monad. Who knows monads? Okay. It's like, I won't spend time explaining monad, but very simple. It's like whenever you do something unsafe that it's not pure, like not repetitive, it must be done once in a particular order. There is a place where you can, one of the places where you have to use monad actually. So this is, and because Java is imperative language, we for instance, when we open file, we don't want to have like opening it few times because Haskell just decided to do that, or other stuff. Then we have to put it inside monad. This monad is called Java. And it's, by the way, it's very, if you know Haskell, it's more or less one-to-one with IO monad, with a difference that in Haskell would be IO of int. So we have something that returns int, and this we say this is something that returns int but works on a class color. This is just more or less like utility thing. We can reuse it so that we have something which is in the Java called this. So on this object we work, but I don't really use it here. So that's how we can, for instance, can have it. There is also like method setRGB. So I say that pixel writer had a possibility with 3 ints to set pixel, and funny thing is that it returns exactly IO monad. So in Eta, I could have written here Java something, but I could as well write IO. So basically, in all these places where I write Java, this is important, the result type, and this is only to say that this is a monad. I could as well write IO of int, but okay, I will leave it like that. And so this way we can, whenever we have a function in Java on some class, we can import this class and we can import this function. This is the way how in Haskell we can use Java. Simple like that.
So this imported class becomes just a type?
Yes.
Which is like
but there is a limitation of that for a moment. There is basically now a limitation. We import only a name of the class. So we only know that there is this object. It doesn't have, the methods are not imported automatically. We have to put them one by one, although right now I'm not sure. There is a tool in Eta basically which generates that. Recently it wasn't yet finished, but maybe it's now. I haven't spent time. FFI importer, simply check. If you have anything with where you want to use a lot of different methods from Java, like hundreds of them, then you would rather use this FFI importer, will generate it for you using this. But and there is a that's how we again just let's say call a method which sets something, but it doesn't really matter if it sets or get. It's just a method from Java which we use as a function. Now, more interesting stuff is how we export. Because in this particular case, it was like Java was calling the Haskell. Not Haskell, okay, Haskell was calling the Java, but I'm not really even sure if in this particular case I was showing. I don't remember, but for sure Java was calling Haskell. And for instance, I can tell that there is a function called newState, which takes some game of life state and returns again IO of game of life state. I'm not really consequent here. But actually here I should have used IO monad instead of Java, I think. But you can basically, whenever I'm importing, I'm mostly using IO. Because this is, for instance, not returning any object, and it's returning object. Now it's a good question. Could have been as well. I'm not really sure if it would work this way. Java IO, this makes no sense in my opinion. Go state. Oh, sorry, I simply forgotten because there is a slight difference, but basically you mostly use IO. In that particular case, if you want to use Java, it's not perfectly documented. I was using that in the past, and I put somewhere a documentation was a slight difference, but mostly I'm not always using it. Sorry, because I just realized that I'm a little bit forgotten if nothing wrong happens. I don't want to spend time on that. But basically, Java is more or less the same as IO. Okay, this and this. So we export. Maybe now interesting, what does it look in code like? Because we have like let's say newState. LifeJay, this thing, yeah? Or maybe I would see, just a moment, fill image. Okay, this would be better. So there is a function that's called fill image XP, and it takes some game state and some pixel writer and returns a new pixel writer. Let's see if we have this function in Eta code. We can go to classes. Now, what I see here are that you want see that because you need a special like IDE like I'm using, IntelliJ, but there will be a class like this, a LifeJay class, and now it's decompiled. So, and I have all those methods, and what you see, those are all static methods. Who knows what a static method in Java is? Okay, so you all know this is like method not on an object, just static, and we have, for instance, somewhere this set, just how was it called? That was fill image. Yeah, and I should have here somewhere fill image XP, and this returns, now this code goes to some Haskell code, which now is crazy. This is Haskell code decompiled to Java. This is all created by Eta, okay? But nevertheless, there is one file which you see LifeJay, which has all those static methods. Just a moment, that wasn't exactly this what I wanted. Sorry, actually I said wrongly. This was this code. This is better. This is for exactly fill image, this one. Because internally it calls fill image XP, this one method I was showing you. But initially from Java we have this. Some int, some pixel writer, and so. Then if I go to Java code, here, a live window, for instance, do I have this fill image? Yes. As you see, my IDE didn't really fully recognize this is a known symbol. It comes from Haskell. This LifeJay class was fully generated by Haskell, has a method fill image. Then I give it some parameter and it's done. So basically, I'm exporting everything which is static method, which more or less makes sense because in Haskell, the functions are more or less like static methods in Java. So this is the thing. Now maybe here in this code there is something crazy because which is also used in the same way when you work with C code in old Haskell with C code. I have had this plane with a state of old cells that are alive, and I have a function like next generation. This function is, where do I see it? Next generation. Just a moment. Make step run. Sorry, that wasn't this what I have to see what was this next make step run. I just make step here. There is a function called new state. So I have a state and I get a new state. But there is one interesting part. This state, if you remember, was fully defined in Haskell. This state is this plane, okay? So this is this data structure which is fully in Haskell. There are two possibilities. Either and I did it, you create the classes in Java which correspond to this plane. So basically that would be like I have a cell, you have to create a normal class in Java which is cell, maybe it has boolean inside, and you have to create class in Java which is row, which has a list of cells, etc., etc. Then you have to do this mapping, and maybe in code of Haskell you would just fill this Java structure from Haskell, which would mean a lot of imports. But actually we don't need those imports. What if we just could pass to Java, this is object which represents my state of the game. This is just object, a magic object for you. Don't look inside. This is an object. And now Java has only possibility to take this object, some magic state, and get a new state from Haskell. Only Haskell knows what's inside. To the Java, this is just something crazy. It is in fact a pointer. Like pointer, it's there, you don't know what's. So, and that was used in C in the same way we do that with Java code and Haskell. And this is exactly the same way. So I will show you. I have something called game of life state, and it uses something called stable pointer. This is a structure which say under some pointer I have some plane. This state of the game, the plane is a state of a game, all those cells, and I create something which is a stable pointer to that. And now the point is, stable pointer is visible in Java as int. So you have like 1, 2, 3, 4, 80. Actually, they are even starting from 1. So those are not really memory pointers. It's not like in C. This is just a sequence number. So, and you will even see that whenever you run this code. In fact, whenever you run it, you should see something. that, okay, new state 80. Actually, I have more code than I wanted. Sorry, just a moment. And new state 81, etc. So, and by the way, when I click again on this window, the new state will be 80. Why? Because I'm freeing the previous one. And basically, there is like a table where there are all states, let's say this pointer stored, and everyone had numbers. So basically, there are like 79 reserved from something, and when I'm getting 80, and then I'm freeing it from time to time, because this is exactly a state which is like you create object on heap somewhere, you give a pointer to Java. Java can now call you back with this pointer, but you want to be sure that there is no memory leak. So whenever, just a moment, whenever I work with Java, I have to not forget from time to time, whenever I use a state and I get a new one, to free the previous state. If I don't do that, well, maybe let's check it. I won't do that. Now. Yeah, you see, you get only new pointers like 95, and that's how you fill the memory to the end. Okay, but nevertheless, this is very interesting. I found this method actually that wasn't very, I needed the help from Eta developers, because it's quite often that I have some procedure in Java and in Haskell, and I don't want to even like massive exchange with Java. Java doesn't have to know all the details about my data structures. It just needs something like pointer. So that's how it works. It's really nice actually, and it saved me a lot of time. Okay, so let's go to so we've seen how to import like a Java class as a type in Haskell, how to import and export functions. There is a, yeah?
So one of the classes you had was the sampling. Forgot it was the life stage, the life, right?
Mm-hmm.
How does it, if you export this to Java,
Mm-hmm.
how does it look like?
Okay.
Is the base class the process?
So the point is, you don't export data types from Haskell to Java. You only export functions.
Okay.
The only way you can do that, because I had such projects, it's vice versa. I have to create the objects, the classes in Java, and then Haskell is working on them because it imports all the structure from Java. So
I would need to create like introspection method, like a combinator in Haskell saying like is dead and is alive.
yeah,
And export these out to Java, and then Java could know.
yeah, more or less like this.
Something like this, right?
And I had such similar projects, and if I did it this way, so all the classes are, let's say, this is like, where is my model? Here you see the model actually is totally in Haskell, and Java is barely touching it, like getting a pointers. But you can have model in Java. In that case, you would create like Java classes, maybe beans or whatever stupid you want, and then you will have a lot of methods to work on that. So but that's not a problem from Haskell. You have to create a lot of imports, which is tedious. But you can, in all your exactly Haskell functions, in Eta functions, you can call Java methods, yeah, as you wish. And I actually do similar stuff, and I have such projects which, let's say, which does this way. Let me show you that. I call it ratpong. Moment. Eta pong.
I have 2 more questions.
Okay. But, okay, sorry, I cannot. But basically, I did it, and it's visible that you'd rather want to avoid that if you don't. But if you have a model, already existing model in Java, then you go this way, okay?
The other question is like, if you're dealing with a big chunk of data,
Mm-hmm.
for example, you want Java to process a big PDF file and just send the information back to us.
Mm-hmm.
So it's like a big byte stream. Is there some trick to do it more efficiently? Is there some way that is advisable by?
But okay, the thing is, this is a very generic question.
If you're dealing with a big byte stream,
Mm-hmm.
are there like recommended ways of transporting lots of data between Haskell and Java.
So
it's like, what type do I use? Do I use by-stream in Haskell?
that's a good question. Okay.
It becomes something like a stream in Java.
Okay. Yeah. That's a good question. I don't have in memory what is the answer to that, but I will look here, documentation, and this is like.
We kind of struggle with it.
Oh, okay. Yeah, but just a moment. This was Java wrapper types, or wasn't it that? No. Basic. There was something like standard mapping of types, and I wasn't sure if there was nothing for bytes. Moment, just data wrapper, converters, Java monad. Oh, here is described Java monad. What it's exactly how it differs from I/O, but I forgot it already. There was some table which described mapping. I don't think it was that. Java primitives. Okay, so you see this is a standard conversion between Java type and I don't see anything for bytes. Actually, so okay, I don't know answer to your question for bytes. I would. Yeah, I would say Slack or Gitter. Yes. I'm sure I haven't had this problem. So, just a moment. Here is Java arrays, but now that is a different. But this is, I think, I don't think it solves your problem. Primitive are okay. Actually, this is the standard. So those conversions are built in. So if you can have like car or byte.
That's sort of a problem because we have a byte stream. We don't want to come. Oh yeah. What's the Haskell type?
Java okay, array type. The question is, this is not really a Haskell. This is an Eta. But you can bet that this one is more performant than maybe I would look for this. I was looking for this, but I didn't know whether it is. Okay, so you have actually here an example how it looks like. Arrange just. I would check if it's performant enough. Yeah, I can't promise you anything, but I would look for this. Okay, so. I won't spend much time, but I want to finish this part of the. So we've seen that Eta is like GHC for JVM. We can more stuff we haven't checked, but who knows the compiler extensions in GHC? Like, okay, I don't know a lot of them, but basically this is actually the problem in Haskell that the Haskell is all GHC is an old one, and through the years there were a lot of like flags in compiler, you enable or disable, you want to support special syntax, like special features or not. This is, for instance, quite common, those ones. And funny, and a good thing is that Eta supports basically all of them. So even in example, you had something like, there was like bank patterns I used, but yeah. So you don't have a problem with that. This is a really cool stuff because typical Haskell projects use a lot of those extensions. So that's cool that all of them, all that I know work in Eta. I'm not sure if there is like a table which says which are not working, but I haven't heard about it. So one more thing, which is also interesting. So you've seen how to do imports. So original GHC as well had foreign import to do C calls, so like native calls for libraries in C. And this is actually from a like float implementation in base GHC Haskell, like built-in float. So you see import is float, not a number, and there is somewhere a function. Sorry, it's not really visible. Okay, this is like import of C function, which is defined like that. And in Eta, there is also this base library, which is written more or less like that, but it's, I would say, via some search and replace. It looks like now the corresponding lines will look like that. Basically, in Java, there is as well float built in, which has a method is none, and yeah, it's called here. So it's one-to-one when it comes to built-in types. Okay, and it's actually was very quickly done. So, but there is a hackage. All those libraries written by people. which contains some C calls, and how to work with that. So they created something really crazy. There is a special project on GitHub called Typeless Package, which contains a lot of sub-projects, patches, let's say, not really sub-projects, and it contains things called patches. So when there is like library quite commonly used text something, this version, then it has like text patch. This is really created by ETA people or by community or by open source, which says this line with this C import is replaced with this Java import. And obviously this has a problem because this is for a very exact version that you want have used. And if you have like 20 versions of library, you need 20 patches, which is like tedious, but already there are a lot of these patches for various versions. So so far, I mostly don't have problems with that because first, only like part of the libraries in Package really use C calls. Actually, I would say, I cannot tell you, but I expect like 5% or something, maybe even less. So this is not a big deal. And those most critical are already basically covered like this. I'm not really satisfied with this method. It's like, it's working, but obviously it's not scalable. What if we create quite often new libraries, new versions, then of course someone has to constantly fill these patches. Oh. But okay, maybe this will get better. Maybe it's already, but I just didn't know. And so basically the summary of this part is like ETA is really as close as you can get to do GHC on Haskell. And I actually tried with some, I didn't have any productive project to play with. I had some like, you know, hobby, small projects, really couple of files in Haskell that I had before. And basically only with one of them I had problem because it was using something with file scanning, and the functions were using like operation system calls, which already were, so far were not patched with this ETA package. But this was very specific thing. So this concludes the first part, and now we go to the really serious and sad stuff, so into the JVM. Okay? Take a deep breath. So what is JVM? We already had this question. Yeah, so on the first part, is something basically, this is something that runs class files, okay? And the question is, what is a class file? Class file has well-defined structure. This is what, if you have a class file, this follows this structure. There is this magic here, which I already told you what's there in this magic.
Cafe baby.
Cafe baby, yes, that's how you recognize class file from Java. And then there is like version, blah, blah, blah. Important stuffs are like here, methods and attributes, etc. Because if we go there, method info, it's like a declaration what kind of methods we have in this. So every class file in we deal, this is like a Java class in a sources. Yeah? And then it has a lot of fields in something we call bytecode. And now what this bytecode is. So bytecode is basically kind of assembly language. If we have a method in Java, let's one step back. This is more where it is. We have a method in Java, we'll have something called code attribute. And this code attribute will have something like just code. Moment, where exactly this is? Here, the code. And this code here will be this. This is only a few of the bytecodes. I think we have something like less than 200 different bytecodes. Surely not really many of them, but just so a load, it's like there is a number 32 which represents this operation. It's 1 byte, and we basically load onto the stack a reference from an array. So we need somewhere some array reference, which is a parameter to that, an index, and then we load on the stack element. Or we push on the stack null, just if someone wants. Or for instance, duplication operation, everybody probably heard about this. This is typical for assembly, like duplicate recent element on stack, like put it twice. Yeah, so there is like such operations. So who sees something interesting about, there is, of course, you will find quickly pages which describe all these opcodes in bytecode. What is interesting about that? Do you see something already with this, from this? Compared to the normal assembly, who knows, who has seen assembly in the past? It is like assembly, but there is one thing very specific to that.
Virtual registers.
Sorry?
Virtual registers.
Okay. Do you see any registers? Actually, so the point is basically, it's like, it's not using registers at all. It's only using stack. So everything is working on stack. You push, like tons of things, push on stack, pop from stack, blah, 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 and like that. This is how bytecode is defined. And so anytime you have any class, actually you should now have some classes, you can decompile it this way. Maybe let's try. So this is like not fully the compilation, but let's go. So I will go to Java code. Maybe first I will go to build classes. Now Java main PL. So you see there is a structure because I used something called packages. Okay, now I have a couple of classes. Maybe this won't be very interesting. So live window class. Oh. Why? Of course, there's this error. So, and now I have decompiled class. And now I see exactly those. For instance, this operation make buttons, where I create buttons on screen. And you see, there is like new. This is like put by the compiler that I'm referencing to the constant 76, and this represents this, for instance, name of the class, and so on. And you see, allowed is taking from the stack, a store is putting on the stack, etc. Allowed 0, allowed 1 means variable 0, variable 1, and then there is like up to 5 predefined. If you want to 6, then there is special operation allowed n with parameter like 6, 7, or 8, whatever. This looks like that. Interesting maybe codes is like invoke static means I invoke static method, then this parameter says where is the name of the definition of the method. Invoke virtual means I invoke virtual methods. Who knows the difference? What is invoke virtual and invoke static? Why there is this difference? Object-oriented programming. So invoke static is like, there is a static function, surely this, I go exactly to this code, I run it. Invoke virtual means there is an object that has this method seed period, like this, but it might be implemented in a subclass differently. You know subclassing, object-oriented programming. So this means that before going to the specific code, first it has to check where is exactly implementation. This is like this late binding. Sorry?
It goes down in inheritance.
Yeah, it's basically overridden in inheritance because maybe there is like there is like hierarchy of these methods. I won't go to that, but basically this is like we have a couple of other invoke, but those are basically those two. Oh, invoke special, you see actually. Invoke special is special because this means we call, but it's used in different places, but it means we call a constructor, we create object. Okay, but nevertheless it looks like that, like there's a special return, and for each method we have this. If it's Java code, I can tell you that you can quickly learn this bytecode. No one needs that, but you can really learn it. It's very simple. So what we typically do, if you have like IDE for Java, any IDE, do it for you automatically. So if I go to the same class, live window, actually that it doesn't even let, oh, this is the compiled. And now you see fully exactly the same code as it was written in Java, mostly exactly without comments, because comments are obviously not there stored. But this is very, very easy. But what if I go to the class that was generated by Eta? Because we have this Eta code, and there are some classes here. So I already shown you, like, this is now like that. This looks way more complex, and this is not even bytecode. All these methods are bytecode, but this is now decompiled, yeah? So maybe, let me even do that in the bytecode. Just to see, cd. Not that. Eta code build, well, classes, Eta main. Okay, now would be like PL. Do I want to do that? Oh, no, actually I want to do to main LifeJay, I think that was, and that was, no, maybe that was, sorry, life rules, okay, rules, and then some class. I don't really, something doesn't, I would say I need the class here.
Oh, your CD.
Ah, yeah, thank you. Okay, but okay, CD is okay. Now Java pmin, okay, should be LifeJay something, or okay, where am I? It was one above. Ah, now I have it. By the way, you see how many classes are here. That's also a problem, but we have to select one of them. Life, maybe rules. I select something. Well, no, I don't remember which good name. 6 was interesting, no? Oh, I don't have, okay, 36, whatever it is. Okay, and there I get some code, blah, blah, blah. Update table func, I will cover that later, but basically this is normal bytecode. One thing maybe, why don't you see all those crazy classes here? Why you see here 3 classes, and if I go to the folder, I have more of them. This is automatically done by Java. Basically, Java has this rule that one class file is one class in Java, but in Java in syntax has something that you can put in one file a class, and inside of that multiple not subclasses, nested classes. Okay, and it happens exactly here. So I have class called LifeJay, and inside I have public static class. Just a moment, I have to go there. There should be like public static class. Yeah. Static class, okay, like this one, generated. And Java simply makes it like that. Then in code, in syntax, in sources, you have this in one file, but on disk it's always split it to multiple. Here, actually, it's IntelliJ is cheating. It's automatically hiding all those plenty of classes to not make me, miss headache, but they are there. So when I'm decompiling it, it combines it again to one source. But you see, you have all of them. So now you already see one small problem. After this Haskell code is converted to Java, it's really hard to see what's what, yeah? Like if you converted Java to bytecode, vice versa was more or less the same code. Like there are sometimes very small shortcuts and small changes, but yeah, obviously you will see in the decompiled class of Java which Java source was that. If you try to now tell me, for instance, which line in Haskell is which of these things, it is really hard. But I will show you later how to do that. But by the way, I don't have a perfect method for that. But basically, yeah, it's doable to some extent. Maybe there is a method that I don't know about it, but it's basically funny. So it's like, it's more or less like you compile some C code to assembly, and then it's really hard to find in assembly where is my method. It's possible if you put debug symbols, but here we don't have them. But okay, so that's the thing. So this looks like that. Let's go to the next point so we can decompile. So bytecode is assembly-like, but it's stack-based. This is very important. So maybe now the problem, interpreting bytecode. Who thinks it would be very slow, this JVM? If we just, because it's stack, it's just we interpret it. It must be slow, yes? Yeah?
It's like 10 to 100 times slower. I just run some.
Okay. What did you compare it?
Just my alternate code solutions in Haskell. So maybe it's a longer observation.
Okay, we'll go to that. Okay, so For one thing, again, there are multiple JVM implementations. I will be referring to Oracle JVM, OpenJDK, which are let's say most common. And it has something called JIT compiler. Who knows what's that? Okay, so you know, what else has JIT compilers like? JavaScript engines as well have them, mostly, modern ones. So just-in-time compilation means while we go through the code, we compile it, because now the funny part, we say that we compile Java with Java-C, with this Gradle, whatever, but we compile it to bytecode. But then comes the second compilation. When we run the Java, it will compile it finally to assembly. Not always, but sometimes. This is also very interesting. Sometimes it will compile it to assembly. And there is a trick of that. So basically, the Oracle JVM, previously the Sun, had used something called hotspot. What the hell is that? It means that it compiles only those parts of code which are heavily used. So if it has like, if you would write like main method with just do this, do this, do this, you will run it, nothing would be compiled to assembly ever, because it just goes run through this. But if you put some for loop, which would be called like 10,000 times, at one moment Java would see, oh, I am interpreting this code quite often. Let's compile it now. And basically this is, by default, it's interpreting a piece of code. If it says, it seems to be used a lot, it compiles it with a first compiler called in the past C1. By the way, this is changing right now. And this code basically like compile it to assembly, but quickly, but good enough. This is like, do not spend much time on optimizations. Just make it. But if this code compiled to assembly with C1 is detected to be even more used, like, and actually there is even a number behind by default which was like 10,000 times. I called it 10,000 times. Then it goes to the second compiler, which is very aggressive in optimization. It is slow, but it tries to create as optimal assembly as possible. Then it goes to C2. And by the way, Java with this assembly uses all the registers that you have. This is, by the way, this is cool, because if you, for instance, compiled something for, I don't know, simple Intel machine, 2 years later comes a new Intel with more registers like SSE, more this vector register, etc. You just get a new JVM and it will use them. Actually, this is happening quite often, that they even make use of those registers better and better. So you compile it once to bytecode, but it might run even like 50% better in few years the same code, because the JVM will get better and will use your hardware better. That's actually a cool thing. And what is also very cool, C1 and C2, they know how your code works. So it means they knew, for instance, in this if, you mostly go to else. You mostly go to else. In this for, actually you typically skipping after the first, you do like break from a loop instantly. If it knows that, it can compile it optimally to your most chosen path. This is like dynamic compilation. The compilation in a runtime has more information about your code than, for instance, static compilation. If you do static compilation like C++, compiler also guesses this. I think it mostly will be this if will be mostly actually true. Then it can optimize it and align code to this, but it can only guess. JVM actually counts it and can use this information. So there are ways where sometimes this assembly created by Java is actually way better than static compilers could do, because it knows more about the code. Of course, after some initial delay, because first, like thousands of times is only done in a runtime, in an interpreted mode, gathers those statistics and only then uses them. Okay? And we can see that print compilation. And this is something you can try. I will show you how. So you didn't manage to, yeah?
So it doesn't look ahead to try and figure anything out. It just runs it and keeps track of what happened in the past.
Yes, that's by default in hotspot. In recent JVMs from Oracle, there is like, something called GRAL, and there is something called like ahead of time compilation. Basically, you take your classes and you create native image ahead of time. It tries to guess. And yeah?
Does it persist profiling data across multiple? Like,
No, that's the problem. Actually, it doesn't. Those statistics are lost. That's the thing everyone is thinking, and so far they've never implemented that. Everyone has decided, wow, that's obvious. Okay, there is, okay, with some classes they do it. Actually, I even disabled it. So there is something called, just a moment. So partially this is done actually, but not to the point you would like to have it. So for common classes, just let me see this. You can read about this parameter, and actually I took it for some reasons because I took it. This sharing means that for some common classes like built in Java, they are already compiled version of them stored somewhere on the file system, and you only have them once. The first time maybe you start any Java project, this will be compiled there and stored. But I don't know exact details. But for some reason I had to disable it in this moment. But by default it's enabled. But it's not nothing about your classes, which actually do matter. It's only about the built-in Java, as far as I know. Yeah, I'm sure because I have this problem actually. And yeah, so let's. So in this gray Java code that you have in the build Gradle, you can in a run you can uncomment this section, print compilation. And now maybe I will. Please. Java code run, it should go. And we should see, by the way, I think I had, just a moment, I had more information than I needed. I actually, you know what, I will disable that for a moment. I already had spoiled my, just a moment, once again. Now I should see only the compilations. Yeah, you exactly see that. So this is a debug from JVM, which says which methods were compiled. And it even says by which compiler. So I can simply tell you that if it's 3, it means the C1 compiler was compiling that. By the way, 1 is as well, as far as I remember, C1. So they're like different. This C1 has also different levels. Like 1 to 3 are C1. Like if the method seems to be never interesting, it's got compiled by one version, but what is interesting, if it's 4, it means this method was really heavily used, and it's now compiled by the best compiler there, like C2. Okay, this is now, and you have more comments here. Okay, made zombies actually. So, but you will see, for instance, that's no difference. There's like string replace method. So replacing as part of the string, of course, it's heavily used somewhere inside quite often. This is like a lot of string methods get compiled very quickly. And now, if I will just, this is also very funny. Just a moment, IntelliJ. I'll try to show you. Even if I go around this cursor, there are methods called by JavaFX. Basically, they trace the cursor of mouse. And the more I move, the more those methods are called. But slowly, all of them become compiled. Depends, yeah. So, for instance, now I start to click, and you see, actually, this is like a tons of things compiling, mostly around JavaFX. You don't really see much Eta code there, but there is somewhere. Finally, yeah.
You have to push the button 10,000 times.
Actually, yeah. So, actually, yes. So, if I had to that was the correct assumption. If everything had to be compiled here, I would have probably to put this button exactly 10,000 times so that the last function. But okay, might be not. There are some exceptions, which means that even after that time it won't be. But those are mostly rare exceptions. We see some more statements here. For instance, made not entrant, as far as I remember, means that now there is a better version of this method, which is like even better compiled, and please don't go into this code again. I'm not really sure because I'm sometimes forgetting. I'm not looking that often at this. Sometimes I'm looking at this if code is incredibly slow, because sometimes it tells me that this method will never be compiled. Then this is a question why, but sometimes this is explained as a warning. For instance, there is like a crazy bytecode that Java cannot compile, etc., etc. So this is the point, and this is good to know what it already says to you when you benchmark Java. When you benchmark it and something is like only once called, you measure the Java only in interpret mode. This is really mostly means will be very slow. So typically, like you have to call something 10,000 times, more or less, to make it as fast as it will be running in the long run. That, by the way, that's also why Java is mostly used on servers. Servers like run for hours, and let's say after first 2 minutes, they compile almost everything, and then they are fast. But if you, for instance, do with Java command line tool, let's take this text file and like grab something. This is typically a horrible idea. Mostly it ends badly because it's like works, 100 times slower than corresponding C code or something like that. But yeah, that's the point. Maybe on the longer file it would be finally almost as fast as C or something like that. Okay, so that was it, but it's good to know about it, how this part of works. But that's not even more about it. So what kind of optimizations are in this hotspot? Because, who knows what the virtual method or inline method is in C++, let's say. Okay, inline. What is inline, Robert?
What is the optimization technique when you replace the code that you call from the function and praises these in the function, kind of a compiler coding test?
Yeah, so normally people assume that if I have a function, if I call it, of course, you put arguments in register on stack, then you call that, you jump there. If it's a small function like adding 2 lungs, maybe this whole operation of jumping there is like costs way more than the function itself. So inlining means don't do the jump, don't put arguments, just I place like macro expand the code here. This is inlining. And in C++, you have a keyword, inline. You say, oh, this function is small. Then I put inline there, okay? And this is like what I've learned in 90s in C++. By the way, now you don't have to do it anymore, but people still do that, mostly. Then you have virtual functions. So virtual functions are polymorphic calls. So if you have a inheritance, object-oriented programming, and you have a base class with some methods, which probably, and you have a subclasses with some other methods, then in C++, if you had, for instance, method m, and you wanted to override it in a subclass with a method m, the first method had to be virtual. It's a special marker for C code, for C++ code, means, oh, be careful, this code could be actually on a runtime calling a different method, could be overridden. Yes, this is the meaning. Why this? Because by default, you don't want to have all the methods virtual. Because if all the methods in C++ were virtual, it means every call, not only I would be putting arguments on stack in registers, jumping, I will be also checking, maybe it's overridden. All the time this check, that would cost a lot C++ code. So they decided to put a special keyword, virtual. You only mark those methods that can be overridden. All the errors are just same call as in C. It means relatively fast. And by the way, you cannot basically mix virtual and inline. It just makes no sense. Although actually, it's now allowed in C++, but this is like tricky thing. C++ will tell you, if you inline virtual method, it only allows you if you have only one exact implementation of that. So you can inline this because there is only one implementation, yeah? But it's statically checked, etc. Of course, inline makes code faster, virtual makes it slower, but enables you polymorphism in C++, meaning you have to choose. Now the Java choice. In Java, you don't have inline keyword at all. There's nothing like this. You don't have virtual keyword. All the functions, methods in Java are virtual, but you can override them. What hotspot does? It basically checks, oh, this method is small. I see the bytecode. It's small, so I will inline it. Then better, this method is, all the methods are polymorphic, but it has only one implementation. So I will just make a direct call. I will not put this special polymorphic call there because it makes no sense. This is even more because this, for instance, in Java exactly has all the information about your code. So, for instance, exactly says maybe even you have like 3. This is a point. You have like class A, which is base, then B, C, D. All they inherit from A, and all they override some method M. So you need polymorphism, but Java says, oh, actually you're only using one of those subclasses. The other ones are just not really used. So again, then JVM will only use, can even inline polymorphic call. Like, because, actually you pretend you are doing polymorphism, but you are exactly using only one implementation. This is in a runtime. And Java put it there. What it does also, it puts a check in case maybe later, an hour later, you actually for the first time run the like class D. Then Java says, oh my God, I already inlined this code. And now the class D came, which actually also has implementation for this common method. All this code that I generated is now not valid. But Java has a special like traps for that, which means, okay, now I invalidate all this past code and I will compile it again, which is basically cool. So it means it can provide you, so the performance of your code depends on a random characteristic. It's basically statistics are generated. It looks what is really used, which code is that. Basically, it's not even there compiled to assembly. So it has a lot more possibilities than actually the static compiler has. I don't say it's as good as static compilers. I wouldn't say that, for instance, at the moment, in the long run, if you have C++ code and Java, Java will be faster. But it's each year, it is faster than the previous Java. And I would say even 20 years ago, there were some algorithms which were already faster in Java. Let's say rather crazy ones, and mostly, I would say, nasty for C++. But I would say now it's when you do typical like array operations, Java is fast enough. It's in the long run. In the first second, it's very slow. So, but you can see more of that. So we see, for instance, inlining. So what it means we'll be now seeing which methods are inlined, not only compiled. This is more or less the same thing. But also, so if you are looking for problems, why the code, like a piece of code is slow, you will check this sometimes. Because it will tell you, for instance, that call is too large. Something is not inlineable. It will just tell you Java wanted to inline this, but said it's not inlineable. It doesn't say why, but you can find it. There are a set of rules which say, and actually you can even, with special flags, to Java, you can change what is inlined. Basically, for instance, there is a choice how big is a method, and it doesn't inline very big ones. But you can say, oh, I want to inline bigger. And you can override this setting. So yeah, then again, I will just be moving and you'll see lots of things happening. And now you even see, like, this is actually what you want to see sometimes, why it's not inline, and then you see, for instance, okay, actually I haven't seen an error, but Kali is to write not inlineable. That's exactly what you're looking for. In case you're doing, for instance, micro benchmarking. Okay, let's go further. So, but going through this is quite tedious job. Just so there are special tools, like you can try this one, but I can tell you it's not really easy to instance. So I encourage you to try this print compilation and inlining on your laptops right now, and I will prepare this JIT-watch, okay? Because this is like. Try. Okay, so I will call JIT-watch. I need, by the way, before I go further, I need that at least 3 persons show me print compilation. Okay, just try it. Everything is prepared in this Java code, and by that time, oh, I forgot about it. Okay, okay, no problem. I will git repo like this. You see that on the screen? GitHub Eta-ws. But of course, there's like now it will be hard for you to, but try. Yeah, you can actually, you can take, if you have anything that runs like Java minus jar, whatever, if you can run it and put your arguments, you don't have, you can do that with any Oracle-based JDK. Let me help.
Actually, next expression.
Okay, you know what can happen actually? So, if you get to this repo, do you know Gradle or something like that? Okay. Clone this repo. Maybe it will be really fast for you, if you are lucky.
You have next there?
I don't. Sorry. But okay, you can try with any Java code. I can help you. Print compilation, print inlining. So, okay, let's. And but that time, I will do some things. So, I don't need print compilation anymore. I do need these ones. So, trace clock.com. Okay, these ones. Okay. Okay. Ooh, that was bad. Just a moment. Okay. So Gitwatch is a project you can download, clone it, but it takes a moment, and you don't have to run it right now. I just want you to show what can you do. So I will do this. Oh my gosh. Oh, it wasn't good enough. Okay, just a moment. Assembly. Did I have it? Aha. Just a moment. Like now. No. Java code run, and it should be better right now. Yeah. I wanted this. So there is a possibility to print all those compiled code, and you now see assembly in the background. This is what I tried to achieve. Now I will go. Okay, just a moment. A few more. Yeah. Maybe more, because it really needs to get hot. I'll try to. So who ran this print, at least print compilation? This is one of the things it's really useful. So because basically, and for instance, I wasn't fixing, but I found this problem in Eta that few of the methods were never compiled because they had some problem with incorrect offsets, and basically they were working, but compiler was saying, oh, this is like incorrect bytecode structure, some metadata doesn't match, so I give up. I will never compile it to assembly. Why? Because in that case, Java assumes maybe there is something wrong, like in security with this code, and says it will be always interpreted, just to be sure. Okay. Now, do I have it better? It's not perfect again. Okay.
Did it just never get compiled?
In that case, it basically never. This was really a problem in performance. Sometimes.
Like these, the ones that you're clicking on, those are yours. So maybe they just didn't get the 10,000.
Yeah, they didn't. I see that. And just a moment. Some of them maybe. Okay, that's the point. For instance, exactly none of them, I think, has compiled to the. I will check this. But here there is something that basically maybe was not JIT compiled. Maybe I will have to run it many more times. Yeah, redraw image, no, not compiled. But I will find other class like what is for sure like JIT compiled, like of course Java, lang, and then you see maybe okay character. Oh, that's actually I had some method that should have been compiled, but I don't see it anymore. Moment, actually it should be one of those. It's not. But okay, I don't want to spend much time, but basically you see here there is a assembly down, and there is a tool which basically allows you to, maybe I will check the method that I'm looking for. As you see, looking in this assembly is not really that funny, but with JIT-watch you can see which method are already compiled and which assembly is there, which bytecode. This is really cool tool. You have to just enable a couple of options like these ones, and it's good to, basically on the JIT-watch page you can see that. And okay, I just say that maybe I would need to run it for many more times. Well, I can do that actually, because I'm sure finally one of those methods will be, I can do it like that. Then something will be for sure called now, because I just hate it to this window. Once again I will start analysis. Okay. Now I think it's a little bit better. I have, but I completely destroyed my computer with that. I have to stop that because I'm running on the VMware. Okay, now it has some compiled method, I think. Just okay, I can put this hide non-JIT. So now you exactly see the typical case where you have bytecode and you have corresponding assembly. So this is a really cool tool. You have like full display, and this tool has really more things. I don't want to spend time. It's good to know if you have problem with performance of some Java system. You have to know how the hotspot works, and then this is one of the tools you want to use simply to see if basically. I can tell you now the point. I don't remember a single time when I used print assembly and it would help me. Really, this code, okay, actually you can read that code if you know assembly, but it's like, of course, like an assembly full of code, and even if you find it's not optimal, I found it, for instance, what then? You can't do much. Change a JVM, I tried it in the past, it's not that nice. Compiling your own version with fixes. This is really old project, and it's like tons of people were there, and if they didn't achieve something, possibility that you can do something better with a classical JVM is really, it's open source, you can try, but it's really hard. For instance, it's way easier to do the same kind of optimizations with ETA. Okay, but nevertheless, it's good to know it exists. So, and what kind of other optimizations, for instance, JVM does? This is, for instance, very important for ETA. We have a Java method which creates some object which has one integer x and then returns this integer. What you see actually, we create on stack an object, then we return integer. So that was actually why we don't simply return this integer like whatever, like what is this object for? If the JVM wasn't smart, anytime you call this method, it would create some object temporary, then it would just forget about it, and then garbage collector would reclaim that. And basically, JVM is sometimes doing that. It means but the problem is, if you do functional programming in Java, or you use ETA, you have millions of those temporary objects, which are like, for a moment created, like for instance, maybe in Haskell, or optional in Java. Optional is like corresponding class to maybe, but this is like a wrapper class. It has behind only one field, But if you do something with optional and at the end you return something and you forget about these optionals, there are methods in Java which create like hundreds of those optionals which are forgotten at the end. If the JVM was every time creating those on a heap, that would be a huge impact on garbage collector. But JVM has something called escape analysis. Actually, it is a broader term. There are a lot of things that go under the escape analysis. One of them is, do we really need objects at the end of this method? If object is created at the beginning of somewhere in the method and is forgotten inside of that, basically it's either not created at all, it's just like integer, or is created on stack. So never goes to heap, garbage collector never knows about it. There are some rules, and basically it works. And this kind of optimization, for instance, makes naive, but okay, in functional code in Java and on JVM way faster than it could be. So it's, yeah. So the problem is there is like a, actually I had somewhere a link to all optimizations in Java, hotspot optimizations. There is like a big page describing what's there. I don't think even it's very recent. This is like 2013 state. There are now more. It's really evolving. The problem is, this means that benchmarking JVM is really hard. Because, for instance, if you do it too short, you have a very incredibly slow results. Because they say how it works like a command line tool, but they don't say how it works in a long run, for instance, as a server. You have to run the code for a longer time. And sometimes, because sometimes in the long run, it can be faster than static compilers. I would say even now it's a rather rare case, but sometimes can be absolutely faster. Why? JVM is smart, for instance, if you do. In a benchmark, people do that. For loop, and then I add something inside the for loop, okay? And then I measure how much time did I spend on that. If you do that in interpreted mode, it will take some time, but after the final optimization, JVM will see, okay, you are counting something, but you never take this result. I will just kill all this code. And then you have this benchmark which says Java is doing this kind of calculations in 0 milliseconds. Oh, that's awesome. And because of that, there are a lot of that benchmark pitfalls. So sometimes Java looks, whoa, this is awesome, incredibly good, but it is only this kind of edge case you had. So this is described. Many problems you have Java. I should have said JVM. There is a way to avoid that. It's called JMH. So basically, it means how to do, this is a framework to do proper benchmarking on JVM. Let's say more or less. You still have to be responsible for many things. You have to read a little bit, but it helps you to create benchmarks that make sense for JVM. And for that, I created a special code here, where I basically kind of in a loop create this new planes, and I create a new generations. And we can simply run it like that. And I can tell you, this benchmark, which I'm doing right now, is totally wrong. Why? I'm doing that inside of a virtual machine. I have 8 Chrome processes. I won't kill them, so this makes no sense. And by the way, in order to make it sensible, I customized parameters to make it very fast for you. Actually, it should be running for minutes, so that the variance of these results will not be as huge as now. I see that this is really now total improper benchmarking. But it basically, if you are going into JVM performance and you are trying, for instance, you have this piece of code that you want to make as performant as possible, you do JMH, and I show you, this is like annotations for JMH. You put your code here, and maybe now you have 2 versions of this code, 3 versions, and only that you should compare it with JMH. That's basically the easiest and the safest way. What JMH does for you, it exactly does this warm up, you see that? So it runs it like a couple of times to warm it to exactly this 10,000 to make it all compiled as good as possible, and then does correct iterations and then calculates some average. It has more, for instance, if you exactly has this problem like I'm doing something in a loop, I don't care about the result, but I don't want to JVM completely ignore this code. It has some special, like, how to call that, helpers, like one is called black hole. So whenever you have something, a value that I calculate, but only for a calculation, then you put it in a black hole so that JVM cannot, black hole is something that succeeds but prevents JVM from eliminating this code. But just read about it. This is very simple. I just put here parameter called black hole, and you can use it like black hole, take this, yeah, black hole, okay, take this. So this is really important, and in case you have these problems of performance in Eta, you need to know about it. Well, okay, actually, how are we with the time? We have 45 minutes because we could do exercise about it, but I don't know. Just a moment, I will check. Okay, maybe let's do a pause for questions, okay? Before I go further, because I just see like I'm now doing a lecture. Maybe who has any questions? Yeah?
Can you talk about code optimization, like working on infinite list and speculative exception?
There will be, I have it. I don't remember in how many minutes, but I have it with some analysis, okay? More like, okay, maybe someone wants to hear about something like tail optimization, something else?
Something about the JDK versions difference,
Okay. Okay. Okay, this is a tough question. Okay, I can answer that. So this is recently a lot of, let's say, problems with that because Oracle changed the license. Now if you wanna use, okay, first of all, we have now officially JVM version 12. And now the policy is that Oracle every 6 months is releasing a JVM new version with some new features, also new features for Java, but you can only use basically it commercially for next 6 months. And they're like, I think each 2-3 years they release something like long-term support. And also recent long-term support, I think it was version 11, so you can run it for a couple of years, but you have to choose. The problem is that Oracle is basically trying to force that people that don't get stuck on some Java version for years, because now there are companies that are still working on Java version 1.4, which was like, I don't know, year 2003. and the problem is even they don't even support them, but this is a problem for the whole community libraries and everything, so they are trying to like partially by licensing push them. So you can use Oracle with this problem that you will be forced, if you want to use it commercially, you will be forced to migrate to the new versions. Migrations in Java mostly are without problems, with some exceptions like JFX. We've seen it today. There are some exceptions, but they are, I would say, rare. It is, and if JavaFX probably is not really that often used, so they maybe basically that's why they decided to drop it from the core. And still you can fix it, but you just need a little bit of time to fix it. So this is a fixable problem because you just simply need some switches, some additional modules. There you have other options, other companies. There is OpenJDK, which is basically Oracle JDK without some few, let's say, codes with performance and something like that. I don't even know the details. And this is OpenJDK, and they provide for you a build, and you can choose it and use it longer. And I'm not really sure about licensing there. So basically, this is a licensing issue. But there are other companies that even build using OpenJDK. So, but basically, for me, as long as you need it, like without crazy performance, commercial support or something like that, maybe as long as you don't need something to cover your back part, just go to OpenJDK and adopt OpenJDK. Yeah, okay. Basically, Oracle provides you some other stuff for that, but yeah, with licensing. But I can honestly tell I'm not really good at this licensing part. This is basically done by some other people. I just don't even wanna read it. It's for me. This is too complex. Yeah. So for me, that's basically I was happy when I seen this page. Just use it, adopt OpenJDK, use it. You have no problem. And by the way, there are other implementations of JVM. I was for years using, I didn't want, but I was using IBM. There is one which is called Azul, but yeah, I won't cover it because they are like, let's say, different. Yeah, there are like too many topics. But basically, I'm not good at licensing. My rule of thumb: OpenJDK, Only if you are working for OpenJDK, if you are working for a big bank and you need some support in paper, because Oracle won't help you anyhow, sorry. But if you need a paper, then go for Oracle, and or you can choose other companies. But I am not specialist in that, even though I worked 20 years with Java. This is not my specialty, the licensing and stuff like that. And in the past, it was just easy. Now it became complex. Okay, so more? Okay, so that was a small break. And now about performance. Okay, I don't know why did I put this slide, but do you know this, more or less? Like modern CPU architecture? You know what is like L1 cache? Really? What is the cache line size of L1? You don't know that. Okay, of course, it depends on the processor, but all current processors like use 64 bytes, but okay. So maybe this is actually affecting the performance of functional programming on JVM, how CPU is organized. So we have CPU core, let's say 4 gigahertz of something. It works on registers. And it's 4 gigahertz fast if it works on registers, because it has all the informations. It's almost that fast if it works with the data in L1 cache, the memory that is very close to the processor. The problem is, what its processor in one moment wants to access something what it's not L1 cache. Then it has to check if it's in L2, which takes a longer time. If it's not in L2, checks in if it's in L3. If it's not there, then it checks in main memory. And by the way, this is very important, processor only operates on data on L1 cache. It means if it finds it in L3, the information from L3 cache will be moved, copied to L1, and then the processor will start. Which is even more funny because it's not copied byte by byte, but with something called cache line, which is at the moment basically standard 64 bytes. So when you randomly, let's say you have like C code, assembly code, which randomly goes through data from memory. Every time you check 1 byte, there will be like 64 bytes together taken from the memory, aligned to some, let's say, aligned. That's very important because there are like huge performance differences. If you use something like, this is a couple of years ago created, there is a source. If you use something from registers or L1, it's like here 5 nanosecond. But if it's not there and you have to refer to L2, then it's 7 nanosecond. But if it's not there, it's L3, it's more. But what's more funny, this represents 100 of these L1 references. This is cost of finding something in main memory. What does it mean if you have 4 gigahertz processor and it constantly operates on, let's say, pieces of data which are spread all over the memory, so they don't fit in the cache. So you constantly read from main memory. Your processor is more or less 400 megahertz fast. It's like, you know, in late 90s, Windows 95, 98. Really, this really degrades almost that much. The memory is very slow compared to CPU in that case. So we want to have this data mostly together, which is the problem for Java, because Java has objects. And everything is a reference. So if you have like small object, which has maybe, I don't know, you have object class point, which has 2 integers, x and y. Cool. They are together, so it's fine. You refer to the first, then you read the second, maybe you read x, then you read y. Y is already in the cache line probably. Cool. But what if you have array of these points? They are objects on heap. One can be here, the other can be there. They are not really together in memory. They might be. Mostly they will be, but you don't have any guarantee. So JVM can be sometimes very slow. And now the problem, what if you have typical functional programming which in JVM means lots of these objects which have references to other. It means jumping in memory a lot. And that is really slowing down. And I don't have any good answer to that at the moment. The people from Oracle JVM are constantly working on that. One of the things they did is this escape analysis. So we don't create that many objects. But still, in the long run, we have some caches, we have bigger structures with a model of our data. And it's typically, if it's in JVM, it's really all over the memory. This makes a problem. And there is like a project Valhalla which will create something like structs in C, which means they will be really together in memory in a flat structure, but it's, I would say, it's probably next 3-4 years before it's there. And we can't really do much about it, but we can check it. So because typically it's very visible, so if you go to this Java, to this, just a moment, oh, JMH, where is JMH? I think I have at the end. So here is JMH, and here I have profilers, yes. You can even display this information. You can see how bad is that to some point. By the way, and this is actually, so I told you in the past that print assembly you basically never use. It's just fun to see, but you don't use this information. But this one is used. It's used, if you see it, it won't be really saying much to you. Okay, I can actually have this result. It looks like that. This is maybe important information. This is so many L1 cache loads, so many L1. This is one of the most important informations. How many cache misses were there? And what you do quite often is you look at your code and you see where those cache misses came from. And of course, it's important how much that time you spend in that. That's actually okay. Here it's 3% is actually already somehow visible. There is more to that. I won't cover this at the moment, but this information comes from so-called performance counter. Every Intel AMD had it. So like you have it in your CPU, and you can check this information. And this is used, for instance, the very famous example is if you have an array, 2D array, two-dimensional array in Java, and you go row by row, then it works fine. If you go vertically, it degrades incredibly, and you exactly see in L1 caches. So what you do typically, you write a method, you see it's slow, you can't find why, all your options are gone, but you then try to rewrite it in a different way. Maybe it's faster, but then you analyze. Maybe this other version is like better in L1, but like more branch misses. Then you try to think what can be your problem. Yeah? Sometimes you see, and this won't show you the solution, but will show you where the problem is. Mostly the problem, for instance, in case of Eta is exactly this spread data, but then at this moment, I would say that still I cannot do much with that, with Eta, but maybe for instance, I'm trying to do some fixes for compiler in Eta. Maybe there will be some method to make it better. Maybe reorganize the internal compiler structures. We'll be talking about it later after the break. So this is how we can do, but this is one of the methods. The other thing that can be used is something called Visual VM. So I'm just showing you the tools. So I will go back to this run. I don't need this. And it shows JVisual VM. Okay, it shows something different. It's actually called for a different reason. One moment. This tool is built in Oracle JDK, but you can download it separately. So some of you already have it. Now, okay. What I will do, I will again do some simulation. Okay. And I can now connect to it. This is actually the place where Java is actually quite cool. I have a project, it's started. Now I connect it to analyze what's happening there. It's already started. And I can check things like, this is interesting, like CPU usage, heap usage, and stuff like that. But what I can do more is here. I can, for instance, start something called sampling CPU. And then I will just do that. I will stop it. And you see, for instance, that there was some method code, and this basically tries to tell me where is my code spending time. And it spends most of the time in something called Eta runtime tank, updatable tank. Who has some idea what this is? Okay, I will get to that. You have some idea? Okay. Yes, yes. When basically this is the same, almost the same structure you have in a normal Haskell. Okay, logically, it's a Java version of that. But for instance, we see here that for some reason, function called getCellValue is very visible here. Now the problem is it visible here because we just use it often, or is it visible here because it's not performant? That's a question to answer. And so I am doing that. I am checking which functions are, let's say, like this is 50. This probably won't help you. That's built in Eta, although actually it makes sense to check what it's doing, but that will be called later. But this is our function. So let's see what it does, and then try to maybe rewrite this function. And actually, I was doing that. For what I found, maybe with that code, that life rules. What I'm doing here, you see, get cell value. I'm taking a plane, then I'm taking a y, then I'm taking a x, and this is actually maybe okay, but the question is, do we have to check those bounds? Maybe they are always maybe they are always correct. That's a good question. Yeah, if there's bound checking, because actually this is like we are checking, but they should never be. No, actually, in this code it makes sense because we are sometimes escaping out of this is so we cannot checking. But what I found, for instance, here is that we do get cell value from plane from x and y, but it means that many times we are selecting the same row. Many times. What if I would say that first I take a row, then from this row I take an x? Actually, if I have changed a little bit implementation, that first I'm taking a row from get cell value, so first y, then x, this whole might be a little bit faster. Actually, I tried to measure it, and the difference was barely visible. But okay, I won't spend much time on that. I just say you that with this, basically, we are trying to guess what's happening and where it's happening. The problem, of course, is what the hell is this? Which function is that? We'll try to get to that. We'll be there in a couple of minutes, maybe after the break. And then you go, for instance, you take all those functions, try to analyze them with JMH, and maybe you will find what's the problem. Basically, typical way of doing that is you prepare different versions of a code and you compare them. Of course, not on such crappy notebook with 10 chromes working constantly. But okay, let's skip that, because I want just to show you as many tools as you need. Maybe you want something to know better. And by the way, okay, I haven't shown you something. Sorry, just a moment. I will show you also this one. So that was sampling CPU. Okay, because this is the problem. Actually, I hate this. I will tell you why. This is a sampling CPU. Oh, I did some moment. What I did? Sorry, my virtual machine just stopped. Yeah, of course. Well, I don't know what has happened, but I lost the. Oh yes, not only the cursor. Actually, I lost the whole input. I will start again. I've forgotten to tell one more thing, which is even more here unfortunate. Okay, I will do that, and because if you go to this, you will see as well that there was a sampler. And by the way, you can as well track memory. It will show you which objects are created, etc., etc. Which again, if you look at Eta code, it's kind of cryptic at the beginning. But you have also a some profiler, which is more or less the same. You know what's the difference between sampler and profiler. And if I even call it, let me do that. Oh, I forgot about something. Sorry, just a moment. I have to stop it. -j, because I will need, let's say, I take 3 gigabytes. This is Java. Why not? Ta-da. Again. Profiler. There's actually the thing you one more, sorry for that. I didn't select the correct JDK version. In that particular case, it makes sense to use the same JDK -d as I am JVisual VM. It's best if it uses the same JDK, and I know what's the problem. I know why it's so slow now, but okay, so slow. Just sorry. I forgot to disable assembly because it's slowing everything quite huge. Again, as you see, there are sometimes stupid problems, but this problem with this call, it's actually quite well described. Okay, well, you will see in the Google that a lot of people report it. And now it should work because basically I used the Java from this Java. Is it really the same? I forgot, but okay, I will see in a moment if the Java was the same, because then it should actually let me profile. Okay, nothing really visible there, but then I will execute. Oh, it will execute something. Yeah, so now it's way slower actually in the UI and everything, but it measures something. And what's the difference between sampling and profiling? Okay, so sampling is, oh my god, I really almost killed the machine. Sampling is, I will do the snapshot. Snapshot, just in case. Okay. Like every 50 milliseconds, there is a signal sent to JVM, and JVM sends, oh, that's my stack trace of all my threads. So it's basically like checkpoint, where are you? And then it's like checked, oh, this thread was in this method, this, and then statistically it's set like 50% of time there was this sampling done, there was a CPU inside of this method, okay? And this is how sampling works. So first of all, if a method is very small but very often used, it might be that the processor will never see that it's there. Especially with inlining, all that stuff, it might be that sampling will never see some things. Although statistically, it's the first thing I typically do, because this is like first, shows me where to look exactly, more detailed. And then there is a profiler, which what does, for each method, it sets something like a start and end point, and then measure how much time you spend in this method. It obviously has a problem. This takes way more, now the whole measuring is actually partially, spoiled by measuring time, because it's put there. So, and this is actually visible here, because I say, for instance, in CPU setting that I profile only those classes, and I don't profile those classes. And in a real profiling session, you put here like, actually you put here a lot. Like, I don't want to profile this, I don't want to profile this, I don't want to profile this, but I want to profile only this, for instance, method and classes. And the funny point is, those that are here are visible, and I were slower instantly. So this is kind of an art where it's like you have living organism like an inductor, and you have to look at something, but you know, the more you touch, the more detailed information you get, but the more you kill what is actually happening. So this is like a slow process where you try to go to the smallest places, but you know the more exact information you get about this small piece, the overall structure becomes completely stupid. That's why you start with sampling. So you want to know, oh, this is my like hot point, and then you go into this hot point, and you typically like set, like don't profile those classes. Actually, in a typical session, I really have a lot here, and then finally you get to maybe this is the method, and finally you see in this method there is a problem with CPU caches or something like that. This is there are a lot of videos. I could show you some couple of mostly funny Java code, which shows where it goes wrong. I couldn't do that with Eta code because it's not that easy. Typically, basically, Eta code is always a little bit tricky, and it's hard to find the better version of that. And even if I find the better is like 2%. It's not really that much. So. But you can see a lot of cool videos, people exactly showing how they change then 2 lines in the code that seem to not make a difference, but they really make, and things like that. So, okay. But there are a lot of things around it. I don't want to spend much time, but you just have to know the tools are, and you see how, if you play with JVM, how deep in the problem you are, because the more detailed measurements you make, the more you destroy actually what's happening. Now to the point. This is something you might use. Dump STG. What is this? But I will cover this later, but you will see that. Where is my dump STG? This is in Eta code. That would be here. Yes. Okay. I will do maybe clean, and we should see that. Just a moment. So you remember all these cryptic symbols, see something, dollar, blah, 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 that were in a disassembled Eta code. We'll get to that. Maybe let's go to build classes. By the way, who made print assembly once again? Print compilation? Who did print compilation? No one? One person? Okay, we'll get to that in a moment. I want to make it, but let's go back to this LifeJay. Okay, not this one class, LifeJay. And then we have something like, what even is that? Blah, blah, maybe I will get to the $6 $6. Okay, slowly, vice versa. We have some cryptic symbols here, like this one. What is that in Haskell? This surely looks like a method in Haskell, but how to find which one is that? So, if we do this dump STG, we have something like that. And who knows what is this? So STG is a language, actually. And how was that? Spineless? Yeah. This is a, like, I would say, minimal functional language. And I will cover this later a little bit. I won't talk about its syntax. But then you can actually see here, for instance, if I have next generation. This is like a method next generation from Haskell was converted to something called STG next generation. And then inside of this code, there are used other symbols. Like I see that I'm using, for instance, make stable. Actually, this is what I'm looking for. Not really yet. Just a moment. Next generation. I think I needed the other one. Okay, this is this actually. So, and then I may see that this code is calling something called like this. Just a moment, I wanted to show something meaningful. Next generation, SAT-SF, SAT-SF. So this is actually not what I wanted to show. Just a moment. This created different code than normally, and I don't know why. And this one is set cell. Okay, just a moment. I will. I will put the I am trying to get to the things I know. Maybe different one. Okay, from here. Do we see any cryptic method name? Like mine lifetime. Actually, for some reason, I was unlucky with getting the sensible name this time, because normally this creates a little bit different version. Like this looks like something. Like, let's see what this would be. A2. Let's see if we can find it out. The problem is that's exactly not easy, and okay, but it's there. For instance, and now we see that this method is something that takes int, cell, pixel writer, and then real word, which actually means this is IO monad. And so probably, for instance, whenever I'm looking at this, this would be method that depends if the cell is alive or dead, creates, sets a pixel or not. Yeah, actually here, set pixel, pixel writer. So I would say this must be a method which is more or less in LifeJay. Let's see where I have LifeJay. LifeJay, do I have a method that that uses pixel writer and yeah, this must be two integers, cell, pixel writer, if was that, then it was setting one state, if other, then other, cell to RGB. Yeah, so this is how our code in Haskell gets translated to some other method, because it actually combined together, was combined with this one, cell to RGB, and created completely different method here. So that's how you find this mapping. The problem is it's not very automatic. I'm just wondering, maybe there is a better method, but I never asked actually people from ETA, because whenever I was analyzing my code, somehow I was able to tell which was that. But now I see this is not really that funny, because for instance, now it's generated for some reason, maybe, I know which reason. We changed the code that I had, and now all the symbols, because you put, by the way, what's your name? Yeah. So you put a better solution for my code. Now all the symbols are different, and I remembered to show you something which I already analyzed, but now I don't find those symbols, because now the numbers are different. But I don't want to spend now time finding them, because it exactly costs a little bit of time, as you see. Because you see, we have these parameters, so what can that be? And basically 3 methods in Haskell can be combined into one, and vice versa. This is really, I will tell you why later. Okay, but let's go further. So we see that the problem that ETA is basically creating a code in bytecode that it's like yeah?
Sorry, really quick, can you just explain a little bit more what the STG was? It looked like unboxed. It's like unboxed?
Yeah.
Kind of look like? It's like a layer of optimization, but it's still valid, essentially Haskell.
Okay, so I'm covering this. So later, but I can tell you simply right now, because you will be. STG is like minimal functional language, and Haskell compiler, original GHC, is going through phases, and in one phase, basically desugars code to this language. Like this is like this minimal. I would say this is a little bit better than Lambda calculus.
It's like System F, I think I read. It was like
I can't actually. I don't know the theory behind it. Like you can go to STG and you can read. I don't want to lie you, because I don't know this theory. I know that basically that's a minimal language that you would like to have that supports state optimization. That you can so that actually there is a language and then you interpret it. But it is assumption that it's a functional language that has a tailcode optimization, which I basically wanted to show you. Okay, and now we get to this point, which hopefully we have to do in 10 minutes. So this is naive Fibonacci, okay? You know this. Everybody understands this Fibonacci. It's perfect. I love it. So we'll create it. By the way, you do Fibonacci. Please. You can do that. Maybe this exercise TCO. So I need that at least 2 persons create this naive Fibonacci. By the way, you can also, if you know how, you can create a better Fibonacci that would use tail-comb optimization, but I don't bother. At least do a naive one. And don't forget about this main at the end, which would, I don't know why I've written it this way, but which would display the result, for instance, for 200. You already started it? It's very busy. But by the way, to keep it, to make it less busy, okay. Yeah? Yeah, this is very busy. Okay, let's see. I did something, I started this process with this XSS 500K. You know what is this? Very simple, stack size. Stack size. So because by default Java has a little bit bigger stack, so it actually can spend a lot of years calculating you for this. Okay, actually not, but
SS is the initial stack size then?
it's every thread has some initial stack, and you define it. Actually, you know, I did it still too much. Let's do it better. I know the real value. That would be way better. And then we fail, or maybe I will. That would be good. And we fail almost instantly because we are out of stack. And as you see, it repeats itself because obviously this is like recursion and we can't do anything. Who has this result? At least it's like hanging. So in the calculation, you second. Okay. So you see. But we can do a little bit better. There are many versions of that. One of this, actually you can do Fibonacci this way. This is, yeah. You have a special function like inner Fibonacci, which takes like a step number, sum and pre-sum. Actually, it should be like pre-sum. Okay, so previous sum. So if it's 0, it means it's 0 steps to be done, and I return a sum. But if it's some n and some sum and pre-sum, I again do a recursive call, but with one less step to be done. What is now sum is what was previously a sum and this pre-sum, and then I put as this pre-sum the previous sum. I hope you understand this algorithm. So it's like more or less like also like a loop, but now still recursion. But now without 2 recursive call, with only 1 recursive call. So at the end. So it's something that some of you actually already asked about it, that could be optimized as tile call. Okay, so now I need that at least one of you implements this tail call. In the meantime, I will compile it. Who has? You, okay, one. I need a second volunteer. You can already run, but do it with this stack size limitation. By the way, don't say anything. If it fails or not, don't say anything. So this is limited stack size. Yeah?
How do you place it in the Atlas command? If the Atlas run on a Cabal object, how quickly
So you want a Atlas Cabal. You can do that. You can. At the Atlas run. I don't know.
Put Java ops in your Cabal file.
But okay, for this, because, moment, you call it just Java. You want.
So I'm just using this.
Mhm.
Wondering if there is a way to do this.
I don't know, but check it. Don't do, check. Surely there is a way, but I don't know. So I think that should be, okay, I have no idea. But you can do itlas exec eta, you know. You were on this first part?
Just build it and do this. So.
But if you don't have eta, you do itlas exec eta, and then fibo hs, and we'll create a jar for you. So we can do the same as I. So other option to build it is like, because sorry, I don't wanna, I think there is a method, but I don't really remember. It would be like this. Itlas exec eta. So who already has this? You. Okay. So if we run this, what will happen is again disaster. Doesn't work. Okay. Something is wrong. But I can tell you, I actually expected this result because we now do a little bit better thing. We'll put this. Oh, I forgot how to put that in. Wasn't it like that? I think like that. Okay, that was like this. Minus, minus, I forgot sometimes this minus, minus in style for parameters. I'm not using that often. Now, let's see if it helped. And you see, the same code now presented a rather huge value, and it worked. What was the difference? Who had spotted the difference? So, I need that at least one person has the same good result as I have. Okay, I think. How you do that? Show me the. Oh, you do easy. 0 to O2 must be O2. You have 0.
I am O2.
Optimization, not 0.
Okay.
You have it?
Compiling.
Sorry? Compile.
Compiling.
Yeah, compiling. Okay, so again, this will be like really good in. So it worked. So this is actually really cool stuff. So it means that our ETA is not that bad at the end. It can optimize it. We only have to use optimization flag. And by the way, GHC works exactly the same way. Okay, I think in a this actually you cannot limit stack, so it will work, but basically it has the same problem. So let's see the method. If we go to the method, this is exactly, I can even tell you, this is actually our Fibonacci as far as I remember. Even here, you see a while loop. So something that was a recursive call is now a while loop. So the people say often that JVM, I really heard it so many times, that JVM cannot be used for functional languages because it doesn't support type call optimization, which is exactly true. But Intel assembly doesn't support type call optimization as well, and bytecode is just assembly. So instead of if you do like one Haskell function is one method, of course, then it will fail. But you can do it like that. You can compile recursive call with the while loop, and it's there. The only thing is that it needs to be done with optimization. And then you see, this is exactly, by the way, it's really readable. You see that you do some plus operation. This is exactly where we sum the things, sum the previous sum and sum. You do minus, which by the way means we are from this n, and so iteration step, we are subtracting 1. And I even think I'm just wondering which is 1 value. This must be main 5. Just let's see. Yeah, this is 1. For instance, it's funny sometimes, but 1 is under disclosure. So.
I've done a test. I just opened GTI, no optimization, and I run main.
And it works.
It works fine.
Yeah.
So it means that.
First of all, in GHC, I don't know which is the default stack. And by the way, maybe GHC, but I don't. Maybe GHC does this optimization by default. I can't really tell you. But I would. This is actually done in STG. I don't know. This is a good question. Maybe GHC does it automatically, but typically they are consistent with ETA. Maybe, okay, maybe, I'm not really sure, but it's something we can analyze. The question is, how much stack do you have in GHC simply? Maybe you have simply more stack than in Java. I cannot tell you. Maybe exactly it does automatically, but okay. Nevertheless, this is like academic problem because whenever you have serious code, you run it with optimizations. Come on, this makes no sense. You do unoptimized code only to do quick compilation, which by the way nowadays makes mostly no sense. Yeah, so this is. I would say this problem. I can understand that maybe there is a inconsistency, but typically they don't do that. Okay, so we see that it works, and I would like to. So better Fibonacci, blah blah blah. It works. One last thing. Oh, we are just 3. After this, maybe we'll make a pause, and we exactly will have last. Oh, not really 2 hours, but something to finish. And at this last part, I will show you ETA parts, and yeah, how, for instance, I have some issue, some fix for ETA compiler, which is a real problem of one user, and I won't do any, let's say, live compiling because I know live coding it will fail, but I will show you how I was solving that. Because it shows, by the way, not only what is ETA, but it's basically the same thing as in Haskell. So it's so you will see a little bit what's in Haskell compiler as well. Yeah. For that, okay. Then so see you in 30 minutes. If you have any questions, I'm right here.
So I don't have an answer back from still trying to run, and I think even I'm running the faster one that should have it. It's been going for, I don't know, 5 minutes, 10 minutes.
That's interesting. But how did you compile it? It was okay. So, you have something like top operation. You see if this is still on top when it's really processing.
Probably that one.
Yeah, this seems to be running, but CPU. How much CPU does it consume? That's exactly how. Wow.
It's just really slow.
Okay, but so the point it is slow. But on the other hand, it doesn't bias out. So the thing is, I cannot explain it. Okay.
I read a little bit about it. I think I might have been
You have a kill function. Okay, but don't do normal kill. Check the pit of this process.
So I want to put it in the background.
Yeah, something like.
Control. I forget. How do you send it to the background?
I don't know. Do you don't have a second terminal or something somehow easy?
Yeah.
The STG stuff, I mean, that basically just looks like regular Haskell. Solutions work, and we'll just have
So
Just know then, yeah. And now do kill -3 and this number. Okay. Now, okay, can you scroll this up? This.
yeah, there.
So you will see here a stack. So where are we? It actually does it unrecursively, which is crazy because you had optimized version, yes?
Yeah, maybe.
Yeah, this is like correct one.
I did it the first time with O2.
Okay, I tell you, kill this and clear the jars. Remove all the jars from this and kill this process and try again with this building because you did everything correctly, but it behaves as the unoptimized version.
Oh, you know what? I think it's because...
You didn't save.
Well, no, I made my own, and this is in your directory, and then I compiled the other one.
Okay, now... Okay, so that's why it was... But you already learned other commands now.